Hello friends, how are you? Hope you all are good and doing well. In this video lecture, we are going to discuss a very important topic which comes under the nuclear and particle physics. This topic is very important from the academic as well as the competitive examination point of view because this topic is used to come in the higher level competitive examination like UPSC-IAS mains optional paper, as well as this topic is also covered by the various university courses. So from all those aspects, this topic gets more attention, and therefore I am here to discuss about this in detail so that every concern regarding this topic may be clear. So let's start the video lecture. Students, myself Virendra Kumar, professor and scientist, and you are watching the Sai Academy channel. Friends, what we are going to cover in this video lecture is related to the beta decay, weak interaction, neutrino, parity violation, radio, radioactive nuclei, and all those concepts related to the radioactive decay coming under the beta decay. So here you can see that there are various questions which are used to ask in the competitive examination, and these questions on the screen you can see is related to the UPSC IAS mains examination. So first question you can see that what is the role of neutrino in the weak interaction of radioactive nuclides? Explain the experimental detection of neutrino. Second question is describe how parity violation was experimentally detected in cobalt-60 beta decay. How was the observed asymmetry in the distribution of emitted electrons explained? Second part of the question is differentiate between K capture and beta decay and explain that what is the internal conversion and how it differs from beta decay. Third question is describe in detail one experiment for the detection of neutrino. What is the difference between neutrino and antineutrino? How is the helicity of neutrino determined? Fourth question explain how neutrino was discovered from the beta decay of radioactive nuclei. Next question what is the internal conversion so that the internal conversion coefficient depend upon the atomic numbers of the nuclei. Next question discuss the stability of nucleus against the beta decay. And seventh question is what is beta decay? Give three examples of beta decay of a nuclei. Explain how neutrino hypothesis helped in explaining conservation of energy momentum and angular momentum. What is Curie plot? How one used Curie plot to set limits on the mass of the neutrino. And next question is what is the role of the neutrino in beta emission? Explain parity violation in beta decay. And last question, comparative account of beta decay, positron emission, electron capture, and inverse beta decay. Friends, you can see that almost every year questions are used to ask related to the beta decay, neutrino, parity violation, internal conversion, and so on. So, from these, we can conclude that this topic is very important and we need to focus on the beta decay and neutrino and related questions which are asked. So we will discuss all these topics related to these questions in this video lecture. Please stay tuned throughout the whole of the video lecture because it is going to be very important and interesting for you all. So let's start one by one. So we will discuss first the weak interaction. Weak interaction in nuclear and particle physics, also called the weak force or weak nuclear force, is one of the four known fundamental forces or interaction. Other three are electromagnetic interaction, strong interaction, and gravitational force. Here you can see that Strong interaction is the nuclear force that binds the nucleus, and electromagnetic force binds atom. Weak force is help in used to help in the radioactive decay of the nuclei, and gravitational force already you know that are the useful for the explanation of the working of our solar system and other planetary motion. Weak interaction, it is the mechanism of interaction between subatomic particles that is responsible for the radioactive decay of the atoms. The weak interaction participates in nuclear fusion, all these phenomena. In the weak interaction, we will discuss the properties. The electrically charged weak interaction is unique in various aspects. It is the only interaction that can change the flavor of the quarks and leptons, that is, of changing one type of quark into the another. These are very elementary particles. It is the only interaction that violates parity symmetry. It is also the only one that violates the charge parity CP symmetry. Both the electrically charged and the electrically neutral interactions are mediated by force carrier particles that have significant masses, an unusual feature which can be explained in the standard model by the Higgs mechanism. So, weak interaction is very important in these all aspects due to their large mass of the mediated force carrier. These carrier particles, also called the W and Z bosons, are short-lived with a lifetime of around 10 to the power minus 24 seconds. Friends, these are the properties of weak interaction. Now we will discuss what is the radioactive decay. In radioactive decay, firstly we will know what is the nuclides. So nuclides are the nuclei of atoms of a specific isotope. They are designated by the number of protons, neutrons, and the energy state of the nucleus. You can write by using the symbol XAZN, where A is the atomic mass, Z is the number of protons, and N is the number of neutrons. To be regarded as distinct, a nuclei must contain enough energy to have a measurable lifetime. Usually, the lifetime should be more than 10 to the power minus 10 seconds. Friends, here you can notice the typical sizes of the atoms and nuclear matters. So you can see that the size of the hydrogen atom is around 1.1 into 10 to the power minus 10 meter, and the size of the proton is 1.7 into 10 to the power minus 15 meter, and where proton is made up of the U and D quarks. And the size of the quark, you can see that it is still smaller than the proton, that is around 10 to the power minus 18 meter. And preon is a point particle, is the component of the quark, and it is very small components of the quarks. You can imagine that if quark is 10 to the power minus 18 meter, so how the preon particles will smaller be. So friends, what is radioactive decay? So radioactive decay is a process under which a unstable nuclei loses its energy in terms of radiation. There are three types of radioactive decay mainly, and those are alpha decay, beta decay, and gamma decay. We will discuss in this video lecture in detail about the beta decay. So, beta decay in nuclear physics is a type of radioactive decay, in which a beta particle, either electron or positron, is emitted from an atom. Emitted beta particles have a continuous kinetic energy spectrum ranging from 0 to the maximum of the available total energy Q, which depends on the parent and daughter nuclear states that participates in the decay. There are mainly two types of beta decay: beta minus decay and beta plus decay. But there is also a decay known as the inverse beta decay, sometimes called electron capture or K capture decay. So we will discuss about all these three types of decay one by one. You can see from these examples that under the alpha decay there is a decrease in the atomic number of 2 and there is a decrease in the atomic mass of 4. So that means alpha particle is emitted during the alpha decay, and in the beta decay case there is an increase of the atomic number by 1. So there is an increase in the atomic number here, and there is no change in the atomic mass. Atomic mass used to remain same in the beta decay. Now, in case of gamma decay, there is neither change in the atomic number nor the atomic mass. Only the gamma radiation is emitted, and nuclei from higher energy comes down to the lower energy state by emitting the gamma radiation and becomes stable. Friends, now we'll be discussing about the beta minus decay. In beta minus decay, when a nucleus emits a beta particle, a neutron in the nucleus, through weak interaction, converts into proton, while emitting an electron and an electron antineutrino. That is, in case of beta minus decay, neutron converts into proton by emitting an electron with electron antineutrino. At the fundamental level, this is caused by the conversion of the negatively charged down quark D to the positively charged up quark U by emission of W minus boson. W minus boson subsequently decays into an electron and an antineutrino. Electron-antineutrino. Beta decay generally occurs in neutron-rich nuclei. You can see by the Feynman diagram for beta minus decay of neutron into proton, electron and electron antineutrino via intermediate W minus boson. Here the neutron is getting converted into the proton, and at the fundamental level down quark is converted into the up quark by the interaction of the W minus boson, and further W minus boson decays into an electron and electron antineutrino. Friends, the big advantage of Feynman diagram is that it tells you what goes into the interaction and what comes out, along with what goes on during the interaction. So here, as you can see, that our neutron is converted into the proton via intermediate boson W minus, which further decay into the electron and antineutrino. So there are rules for Feynman diagram pictorial presentation. The first rule is particles are represented using the straight lines with arrow on them. So here neutron is getting converted into the proton. So we are representing this with the help of the arrow. Exchange particles are represented using the wavy lines. So exchange particles omega boson W boson is represented with the wavy lines. They actually move from left to the right with first action happening on the left and the last happening on the right. The particle creation and annihilation occurs where the lines come together. Exchange particles usually move left to the right unless there is an arrow above the wavy line that indicates it is moving in a different direction. So these are the 5 rules for drawing a Feynman diagram for presenting the beta decay or any interaction or any weak interaction in terms of the Feynman diagram. Now we will discuss about the beta plus decay. So friends, beta plus decay type of beta decay in which a proton P is converted via weak force to a neutron. So here proton is converted into neutron with the help of extra energy and via the weak force or weak exchange particle which further decay into the positron plus neutrino. Unlike beta minus decay, beta plus decay cannot occur in isolation because it requires energy. The mass of the neutron is bigger than the ma- mass of the proton. To get the equilibrium on both sides, there is a need of extra energy. Therefore, the beta plus decay cannot occur in isolation. Beta plus decay can only happen inside nuclei when the value of the bending energy of the mother nucleus is less than that of the daughter nucleus. Examples of beta plus decay: when carbon nucleus C6 gets converted into the boron 5, there is an emission of beta plus decay with neutrino and excess energy 0.96 million electron volt. Positron emission happens when up quark changes into down quark. We can understand this by the help of the Feynman diagram. Here you can see that proton is proton is getting converted into the neutron via the interaction of the exchange particle, that is the W plus boson, which further decay into the positron and the emission of the neutrino. Friends, this is the equation for the beta plus decay. It is worthy to note that isotopes which increase in mass number under the conversion of a proton to a neutron or which decrease by less than 2 MeV mass do not spontaneously decay by positron emission, where 2 MeC square is equal to 1.022 million electron volt. Friends, now I will discuss you about the energy spectrum of beta decay. You can see from the diagram that for the most of the beta particles, the kinetic energy is less. That means large number of beta particles fall in the low kinetic energy range and the spectrum is continuous. That means beta spectrum of energy value Q for the beta particles is continuous because the total energy of the beta decay process is divided into the electron, antineutrino, and the recoiling nuclide. Not only the electron is taking away all of the energy, but it is divided into the electron, antineutrino, and recoiling nuclide. A typical Q value is found to be around 1 million electron volt, but it can range from few kilo electron volt to a few tens of million electron volt. If only electron carried away all the energy emitted, the graph would be like this blue line as shown in this diagram. Since the rest mass energy of the electron is about 511 kilo electron volt, that means 0.511 million electron volt, the most energetic beta particles have speed close to the speed of the light. Friends, now we'll discuss about the electron capture or K capture. So, K capture or electron capture is a process in which a proton-rich nuclide absorbs an inner atomic electron, changing a nuclear proton to neutron, and simultaneously emits a neutrino following various photon emissions in order to allow the energy of the atom to fall to the ground state of the new nuclide. However, in proton-rich nuclei, where the energy difference between the initial and final state is less than 2 MeC square, that is equal to 1.022 million electron volt, then electron capture is energetically favored than the beta plus decay. In this case, K capture is the sole decay mode. Therefore, the condition for the electron capture or K capture is proton-rich nuclei energy difference. That means nuclei should be proton rich and energy difference between the initial state and final state should be less than 2 MeC square. The process usually occurs when the atom is bombarded with high energy electrons. If the collision ejects an inner shell electron, an electron from a higher level will quickly drop to this lower level to fill the vacancy, and in that case, there is an emission of the X-ray photon. That photon is known as the Roentgen photon. But sometimes this energy is transferred to another electron. Here you can see that this electron is captured by the proton, and because of this there is a creation of vacuum, there is a creation of hole here. To fill this gap, an electron jumps from higher level to the lower level, and because of this K alpha X-ray photon is emitted, and if this photon is utilized in transferring the energy to another electron here, then an electron is emitted, ejected from the atom, and that electron is known as Auger electron. And you can see here that the energy of the K alpha X-ray photon can be utilized in terms of the electron bending energy, energy of the Auger electron, and the photon energy emitted h nu. So friends, in the K capture, we can write equation K capture equation can be written as energy plus proton plus electron is equal to neutron plus neutrino. Example of the K capture is given by the rubidium conversion into the krypton. That means 0.9 million electron volt energy plus rubidium 3783 comes into the process of electron capture, and that converts into the krypton 3683 that emits neutron, and that is converted into the neutron, and there is emission of the neutrino. So in this way we see that there is a decrease of atomic number and there is no change in the atomic mass. That means there is a conversion of proton to neutron. Here I have shown with the help of the Feynman diagram that proton is converted into the neutron via the weak energy interaction by the W plus boson that converts into the electron and the neutrino. It is worthy to note that a free proton cannot normally be changed to a free neutron by this process, as mass of the neutron is more than that of the proton. Therefore, proton and neutron must be a part of a larger nuclei so that the electron capture or K capture happen. Friends, I hope you are getting the lecture. Friends, now I will discuss a little about the inverse beta decay process. So you can here see that from equation 1 and 3 that electron capture by a nuclear proton is equivalent to a proton's emission of positron. That means emission of positron by proton is similar to the capture of electron by the proton. In both cases, there is a emission of neutrino. Similarly, you can see that the absorption of an antineutrino is equivalent to the emission of a neutrino and vice versa. This is known as the inverse beta decay. In this, neutrino is captured instead of electron in case of K capture. Inverse beta decay have extremely low probabilities, which is why neutrino and antineutrinos are able to pass through vast amount of matter. But these probabilities are not zero. Friends, now let us talk about the internal conversion. What is internal conversion? Internal conversion is a radioactive decay process where an excited nucleus interacts with an electron in one of the lower atomic orbitals, causing the electron to be emitted from the atom. Thus, in an internal conversion process, a high energy electron is emitted from the radioactive atom but without decay of beta. That means without beta decay. Since no beta decay takes place in internal conversion, the element atomic number does not change, as in the case of the gamma decay. You know that there is no change of the atomic number in the gamma decay. Not even the atomic mass is changed in the gamma decay. Thus, no transmutation of one element to another takes place. Also, no neutrino is emitted in internal conversion. Internally converted electrons, which carry a fixed fraction of the characteristic decay energy, have a well-specified discrete energy, like spectra. Energy spectrum of the internally converted electron is a sharp peak, while the energy spectrum of beta particle with a broad hump extending to a maximum decay energy value. In the internal conversion process, the wave function of an inner shell electron penetrates the nucleus and takes the energy of the nuclear transition without an intermediate gamma ray being produced first. So, what is the condition for internal conversion? So, friends, there are certain conditions for the internal conversion. Internal conversion is favored when the energy gap between the nuclear levels is small and is also the primary mode of de-excitation from zero level transition. It is the predominant mode of de-excitation whenever the initial and final states are the same. The tendency towards internal conversion can be determined by the internal conversion coefficient, and which is the ratio of the de-excitation that go by the emission of electrons to those that go by the gamma emission. That is, internal conversion coefficient can be given by E by gamma, where E is the rate of conversion electron and gamma is the rate of gamma ray emissions. Friends, if you have any doubt regarding this concept, or if you have any query, please let me know by comment. Friends, I hope that you enjoyed this video lecture, and I also hope that this video lecture will be fruitful for you. And if you are watching the Sai Academy for the first time, please don't forget to subscribe the channel and please press the bell icon also so that you can get the notification of the upcoming video on the time. And please share this video with your friends and colleagues so that they can also get benefited. The remaining portion of this video lecture I will cover in the next video lecture. For that, please stay tuned and subscribe the Sai Academy channel. Till then, thank you friends. Bye bye.